Hi, my name is Matt. Now I have some time. I thought I would share some projects with you. This video details a project about how Bluetooth can be used to trigger pictures or screenshots on multiple smartphones and shows how the phone images are converted into time-lapse videos. The intention of this video is to provide you with the information and custom code for you to have a go at this project yourself. Refer to the links in the description for more information on the hardware and software that features in the following project run-through. Bluetooth allows the use of old smartphones to make good quality time-lapses, like the Benchy clip running now. The real Benchy part of the clip was made using an iPhone 6s from 2016. The other parts of the clip were made using screenshots on two other devices, triggered at the same time as the iPhone. The Benchy shows that old phones are a useful resource in making time-lapses. In fact, all the smartphones used in this project are upgrade cast-offs given to me for free. Bluetooth allows device screenshots to be used to make time-lapses, just like regular pictures. Python code was developed for the project that enables a Raspberry Pi using Bluetooth to connect and trigger image captures on smartphones using software commands. When used in 3D printing, the G code that executes the print triggers the smartphones at the end of each print layer. Slicer software is used to add a few lines of control code to each layer that automates the image capture process. When a Timelapse run is completed, each connected smartphone has a stored image sequence that shows the growth of the printed part. These images are converted to a time-lapse video using software running on a PC. Free open source software is used for all project functional blocks, from image capture through to time-lapse video creation. The project could use a wide range of single-board computers, but Raspberry Pi models 1 to 4 are preferred, as they've all been tested and are suitable for use in this project. This introduction has skipped a lot of the project detail, because I wanted to show you the results of using the project system early on in this video. The next section shows a short time-lapse compilation made with smartphones and tablets. These devices were clamped around the envelope of a 3D printer using a home-built frame, and the smartphones and tablets were connected using Bluetooth. Execution of the G code for each printed part simultaneously triggered image captures on up to 4 devices. On print completion, the time-lapse videos produced for each device showed the printed part, as seen from different viewpoints. The time-lapse compilation, which is up next, features several parts and shows each part captured at the same time using multiple smartphones. These parts make up a custom assembly that is demonstrated at the end of the compilation. All the time-lapses shown in this video were made using Android and iOS devices, wirelessly triggered by a Raspberry Pi using Bluetooth. With the explainer over, it's now time to see the kind of time-lapse videos that can be made using free software and some old smartphones. The PoleDocker assembly featured in the timelapse stores a spray mop used to clean floors in our home. This mop model weighs up to 2 kilograms or 5 pounds and was made to protect a mop assembly joint and enable convenient storage. The mop is docked in position and is prevented from falling off or rotating, which makes it suitable for use on a moving door. The compilation shows that you can produce high-resolution time-lapses using a range of old smartphones. This was anticipated as the smartphone cameras taking the pictures are all 12 megapixel types that exceed the pixel resolution required to make 4K video. Setting the camera apps into 16:9 aspect ratio effectively crops the images to native 4K format. This enables smartphone image sequences to be rendered to 4K video. You can also render to other 16:9 formats such as 1080p, but 4K video is the native format for the cameras used. The camera apps are all left in the default automatic mode that makes them point and shoot devices. This simplifies the time-lapse setup. When combined with wireless triggering and a large storage capacity, it makes them ideal for time-lapse use. The project is effectively a software download and setup exercise on a Raspberry Pi and a PC. Rather than oversimplify the process for the purposes of a punchy YouTube video, I will post follow-up videos to step you through the setup process, starting with a Raspberry Pi and a blank SD card. The intention is to take you logically through the setup to get you up and running, and is best done using more detailed subject videos. These videos are in production now and will be posted in the coming weeks. To give you some idea of what the project is about, I'll now briefly run through the key hardware and software required, and then set up and run a time-lapse using a basic system. After the time-lapse run, a quick run through of how smartphone images are processed into a time-lapse video will complete the project overview. By the end of the video, you will be able to judge if this is a project for you. Setting up a system is straightforward and mainly involves downloading and installing software. Programming skills are not needed to complete the project, but modifying script files using a text editor is required. The follow-up videos will provide the details and instructions necessary to create your own system. The project is general enough to use a wide range of similar print or computer hardware, and you're not restricted to using the equipment that features in this video. In general terms, your printer needs to be an FDM type that has a USB comms port and be able to be controlled using Print Run or OctoPrint. You can use iOS and Android devices, but you will need some means of rigidly mounting them for 3D print use. If there is demand, I'll post a video on the camera frame arrangement used to make the time-lapse compilation. A PC, Mac or Linux computer installed with Kdenlive and PrusaSlicer is required. You need to check that PrusaSlicer supports your printer. Alternatively, if your slicer can easily add layer change G-code, then use this instead. You'll need access to the internet and a wired network. Wi-Fi is useful but not essential. A USB webcam is used in this setup, but this is optional. A basic Pi time-lapse system requires only an Ethernet connection and a printer USB connection. The project uses the most common Pi models installed with the Raspberry Pi operating system. The Pi is set up for headless operation and implements a compact, low-power system. The Pi model used will determine the project control software that will be installed. In general terms, Print Run will be used on Pi 1 and 2 models, and OctoPrint will be used on Pi 3 models and above. Pi 1 and 2 models require a USB Bluetooth dongle. The remaining Pi models use a Bluetooth adapter embedded in the hardware. Print Run and OctoPrint are useful for loading and printing G-code using a network connection, which is a key reason for their use in my setup. In terms of this project, both apps can run Bluetooth image capture scripts from within G-code, meaning the Timelapse system is controlled entirely by software. VNC and SSH remote access software are used to interact with the headless Pi. These programs are used in setting up and running the project software. A follow-up video will deal with installation and setup of both programs. For the purposes of demonstrating a 3D print timelapse, the system comprises of a PC, a headless Raspberry Pi 4, a Prusa Mini Plus, 2 iPhones, a smartphone holder, and a webcam. In this setup, a power over the Ethernet adapter is used to power the Pi. The Pi and PC software are set up for timelapse operation using configuration files created for the demonstration hardware. You can connect to a maximum of 4 Bluetooth devices with the current project software. More connections are possible, but this is one for a future video. In this demonstration, 2 smartphones will be used, one taking pictures, the other capturing time. The smartphones that appear on the PC screen in this footage are provided by a screen mirroring app that uses Wi-Fi. This app is not required for the project, and its primary purpose is to allow smartphone interactions to be displayed and screen recorded alongside the setup of PC and Raspberry Pi software. The app is a more convenient method than having to provide separate videos of a phone screen, particularly when multiple phones are being used. This app is not free software, but is low cost and was purchased to assist with making videos with smartphone content. This app was also used as a combined webcam and camera, especially on older Pi systems that can't run OctoPrint, and features in this role throughout this video. For the purposes of this video, I will quickly step you through the following demonstration. The follow-up videos will take you through step by step and provide more detail. With the system connected and powered up, running a timelapse is a straightforward procedure. The first step is to run OctoPrint and check the printer is connected and communicating. Older Pi models will run Print Run at this step, but OctoPrint is used due to the use of a Pi 4. With the printer connected, communication is tested by homing all the axes, and the built-in webcam and OctoPrint allows checking for movement. With the printer ready to run, the next step is to run VNC and start the Bluetooth server. The server allows for connection and disconnection of the smartphones using Bluetooth. Separate device triggering scripts are used to capture images. The server app is custom to this project and will be covered in detail in a follow-up video. It will be made available for download to coincide with the release of the video. With the server running, the phones are connected and the image capture apps set up for the timelapse. The screen mirroring app and cursor are used to demonstrate the setup of the 2 smartphones. The cursor exactly mimics the finger gestures used to set up the actual smartphones and is done to replicate the setup process on the mirrored phones. Following connection, one smartphone is set to capture the time, the other is set to take pictures. Then it's back to OctoPrint to test phone connection and triggering using the system command for this two-phone setup. Testing is done by triggering capture commands using keyboard entry in OctoPrint's terminal. The screen activity on the mirrored smartphones and terminal messages confirms the status of command execution. The command used at this step is embedded into the G-code that will trigger the smartphones during printing, so we can proceed to the next step as captures are triggered correctly. Now it's time to run PrusaSlicer and load the Timelapse Benchy. Slicing it and sending it to the printer using OctoPrint's network printing capability starts the Timelapse Run. Back to OctoPrint, and a quick check of the print status window and the rising temperatures inform that the Timelapse is running. Checks that image captures are triggered on the smartphones at the end of the first few print layers gives confidence that all is working as intended. I sped up some of this footage to improve the flow of the narrative during this run through. That's it, the printer takes care of the rest and automatically captures the images on the smartphones. Time to do something else for a few hours. The intention of this run through is to show you that running a timelapse is straightforward. Running repeat timelapses is a matter of cleaning the print bed, followed by a few mouse clicks. The main project activity is installing and setting up the project software to be able to run the timelapse as demonstrated. A red Benchy was shown in the introduction of this video being timelapse processed using Kdenlive. As the Benchy image sequence has already been imported, I'll continue from this point and import a clock image sequence captured at the same time as the Benchy. I'll use this clock sequence to make a composite video of the Benchy with an on-screen clock. This is a smartphone alternative to the use of real clocks that feature in many timelapses. To do this requires the use of some of Kdenlive's video effects, and will also show how screenshots are processed just like standard pictures. Starting with the existing Kdenlive Benchy project, the first stage is to import the clock image sequence that has been stored in a local folder. This also works for cloud-based storage. Navigating to the folder, import just requires the selection of the first image captured, and Kdenlive does the rest. Import takes seconds for the files shown here. In this demonstration, the clock image captures the time at the end of each Benchy layer. As there are 360 layers in the sliced part, there should be 360 clock images. You can check for this in Kdenlive at import time, or use the Clip Properties tab to check that the run has the correct image count. As this clock is going to be used to overlay onto Benchy footage, some means of removing the black background surrounding the clock is required. The black background needs to be converted to a transparent background, and the crop with padding effect can be applied to do this. Use of the circle option makes this convenient for the clock. Fine adjustment of this circular crop will be done after the next step. I'm going to place the clock in the upper right corner of the video, so the transform effect is used to scale and move the clock to do this. Fine adjustment of the circular crop completes the procedure. The composite video can now be rendered. Whilst this is happening, the video can be tested by playing the timeline. After a few minutes, the rendering has finished, and it's just a case of locating the video and running it to observe the composite effect. You can then add to it and edit the clip to make further videos. This demonstration used some of the Kdenlive effects that were used to make the Timelapse compilation. A follow-up video will take you through this again in detail and include other effects not shown here. I have quickly gone through the running of a time-lapse and the creation of videos using captured time-lapse images. This was done to give you a flavour of the project and preview some of the project system hardware and software required. The follow-up videos will be released over the coming weeks, and I'll put up the Bluetooth code online as soon as it's been tidied up and documented to an acceptable standard. The follow-up videos will cover these core project tasks. It is straightforward to get to a working system, and the videos are intended to pass on knowledge for you to take further. The video content may change depending on feedback, and I anticipate a few videos based on the project task list will suit most viewers' requirements. The custom project code implements a Bluetooth keyboard, and you can remotely control smartphones with the use of a mirroring app, which is demonstrated shortly. Smartphone remote control can be done with any Bluetooth keyboard, but the use of the Pi as implemented by the project allows you to send keyboard codes using software commands. This allows for the automation of other device functions that can be applied to other applications. The details are for another day, but I will close out this video with an overview of the possibilities. That's it for now, and thanks for watching. I hope to see you next time.